Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to settle in. Let your body relax wherever you are. Adjust your pillow. There's no hurry. We have all the time we need. Where in the world are you watching from? A quiet room as the evening settles in? Perhaps a cozy space where the day is finally winding down? Wherever you are, you're exactly where you need to be. Tonight we're going to explore something remarkable. We finally figured out how big our home galaxy really is. For decades, astronomers have been measuring the Milky Way, trying to understand its true size and structure. And now, with new telescopes and new techniques, we have answers that would have seemed impossible just a generation ago. We'll discover that our galaxy is far larger than we thought, understand how scientists measured something we're inside of, and contemplate what it means to finally know the dimensions of our cosmic home. But don't worry. This isn't going to be an overwhelming flood of numbers and technical details. Instead, we'll move slowly and carefully through one of astronomy's greatest achievements, learning how we mapped our galaxy from the inside, how we discovered we live in a galactic giant, and what this tells us about our place in the universe. By the end, I think you'll find a deep appreciation for both the scale of our galaxy and the ingenuity of the people who measured it. If you enjoy these calm explorations of cosmic discoveries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of curious minds. So settle in, let your shoulders drop, take a slow, deep breath, and let it out even more slowly. And let's begin our slow drift through the vast expanse of the Milky Way, our island home among billions of galaxies. There's nowhere you need to be. Just listen and let the story unfold. Let your thoughts wander among the 100 billion stars that surround us. Let's start with a simple question that turns out to be remarkably difficult to answer. How big is the Milky Way? It seems like something we should be able to measure easily, but there's a fundamental problem. We're inside it. Imagine trying to measure the size of a forest while standing in the middle of it. Trees surround you in every direction. Some are close, some are far. Fog and undergrowth block your view of the distant edges. You can't see the forest from outside, can't step back and get a clear picture of its boundaries. That's our situation with the Milky Way. We live on a small planet, orbiting an ordinary star located about halfway out from the galaxy's centre in one of its spiral arms. When we look at the night sky, we see the Milky Way as a band of light stretching across the darkness, the combined glow of billions of stars too distant to distinguish individually. But that band doesn't tell us where the edges are, how far the galaxy extends, or what its true shape might be. For most of human history, people didn't even know the Milky Way was a galaxy. The ancient Greeks called it Galaxias Kyklos, the Milky Circle, and thought it might be a cloud of some kind. Medieval scholars debated whether it was atmospheric or celestial. It wasn't until the early 20th century that we definitively proved the Milky Way as a vast island of stars, one galaxy among countless others in the universe. But even after we knew it was a galaxy, measuring its size remained challenging. Early estimates varied wildly. Some astronomers in the 1920s thought the Milky Way was about 30,000 light-years across. Others argued for 100,000 light-years or more. The uncertainty was enormous, factors of 2 or 3 difference between estimates. The problem is that measuring distances in space is hard. When you look at a star in the night sky, you can measure its brightness and colour, but you can't immediately tell how far away it is. A bright star might be intrinsically luminous but distant, or it might be relatively dim but nearby. Without knowing the distance, you can't map where things are, and without a map, you can't determine the galaxy's size. Each technique had its own range and limitations. Parallax works well for stars within a few hundred light-years, but becomes too imprecise beyond that. Variable stars extend the range to thousands or tens of thousands of light-years. Other methods can reach even farther, but each step introduces more uncertainty. By the late 20th century, astronomers had converged on a rough picture. The Milky Way is a spiral galaxy with a disk of stars, gas and dust about 100,000 light-years across and a few thousand light-years thick. A bulge of older stars sits at the centre, and a spherical halo of ancient stars and globular clusters surrounds the disk. The Sun sits about 26,000 light-years from the centre, roughly halfway out. But this picture had uncertainties. The exact size of the disk was unclear. Did it have a sharp edge, or did it fade gradually into intergalactic space? How far did the halo extend? And what about dark matter, the invisible substance that makes up most of the galaxy's mass? How far did the dark matter halo reach? These weren't just academic questions. The size of the Milky Way affects our understanding of galaxy formation and evolution. It determines how we compare our galaxy to others. It influences calculations of how many stars the Milky Way contains, how much mass it has, and how it interacts with neighbouring galaxies. And there was something else, something that recent observations have revealed. The Milky Way might be significantly larger than we thought. New measurements, new techniques, new telescopes have pushed the boundaries outward, showing that our galaxy extends much farther than earlier estimates suggested. This is the story we're going to explore together. How we measured our galaxy, how we discovered it's bigger than we realised, and what this means for our understanding of our cosmic home. It's a story of patient observation, clever techniques, and the gradual realisation that we live in a galactic giant, one of the largest spiral galaxies in our region of the universe. Let that settle for a moment. We're going to take our time with this, moving gently through the measurements and discoveries, building up a complete picture of the Milky Way's size. There's no rush. Just breathe, relax, and let the cosmic scale wash over you. To understand how big the Milky Way is, we first need to understand what it looks like, and that means thinking about the disk, the flat, rotating structure where most of the stars, including our Sun, reside. The disk is where the action happens in a spiral galaxy. It's where new stars are being born in vast clouds of gas and dust. It's where the beautiful spiral arms wind outward from the centre, creating the iconic shape we see in images of other galaxies. It's where most of the visible light comes from, and it's where we live. When you look at the Milky Way band in a dark night sky, you're looking edgewise through the disk. We're embedded in it, so we see it as a strip of light circling the sky. If we could step outside and view the Milky Way from above, we'd see a stunning spiral structure, arms of stars and glowing nebulae winding outward from a bright central bulge. The disk isn't uniform. It has structure, layers, variations. There's a thin disk where most of the stars reside, concentrated in a layer only about 1,000 light-years thick. Within that thin disk, the younger stars, the bright blue giants and the star-forming regions, are even more concentrated, in a layer just a few hundred light-years thick. Then there's the thick disk, a population of older stars extending about 3,000 light-years above and below the midplane. These stars are billions of years old, formed when the galaxy was younger. They have different compositions, different orbits, different stories to tell about the Milky Way's history. The Sun orbits in the thin disk, moving at about 220 kilometers per second around the Galactic Center. It takes roughly 225 million years to complete one orbit, a period sometimes called a galactic year. In the 4.6 billion years since the Sun formed, it has completed about 20 orbits. 20 circuits around the galaxy. As the disk rotates, it doesn't turn like a solid wheel. Different parts rotate at different speeds. Stars closer to the centre orbit faster, stars farther out orbit slower. This differential rotation is what creates and maintains the spiral arms, beautiful patterns that persist even though the stars themselves move through the arms, rather than staying in them. The spiral arms are density waves, regions where stars and gas bunch up temporarily due to the gravitational dynamics of the disk. As stars orbit the galaxy, they slow down slightly when they enter a spiral arm, bunch together with other stars, then speed up again as they leave. It's like cars on a highway slowing down in traffic and then accelerating once the congestion clears. The dust, tiny solid particles of carbon, silicon and other elements, blocks visible light. This is why we can't see all the way across the galaxy in optical wavelengths. The dust absorbs and scatters starlight, creating dark lanes and patches in the Milky Way band. But infrared light passes through dust more easily, so infrared telescopes can peer deeper into dusty regions, revealing what optical telescopes cannot see. For decades, astronomers thought the disk extended about 50,000 light-years from the Galactic Center, making the total diameter about 100,000 light-years. This was based on observations of stars, gas and dust, tracking how their density falls off with distance from the center. But measuring where the disk ends is tricky. It doesn't have a sharp edge. Instead, the density of stars gradually decreases as you move outward. At some point, you reach a region where stars become so sparse that it's hard to say whether you're still in the disk or have transitioned to the halo, the spherical distribution of stars that surrounds the disk. Recent observations have pushed this boundary farther out. Surveys mapping millions of stars have found disk stars at distances of 60,000, 70,000, even 80,000 light-years from the center. The disk is larger than we thought, extending well beyond the old estimates. But defining where it ends is partly a matter of convention. Do you measure to the point where star density drops to some particular value? Do you look for the farthest disk stars, even if they're rare outliers? Different definitions give different answers. What's clear is that the disk is vast, a structure containing hundreds of billions of stars, stretching across a diameter that's now measured at closer to 170,000 to 200,000 light-years when you include the outer reaches. That's nearly twice the old estimate of 100,000 light-years. This expanded disk is one of the key discoveries that has changed our understanding of the Milky Way's size. We're not living in a medium-sized spiral galaxy. We're living in a giant, one of the largest disk galaxies in our cosmic neighbourhood. Beyond the disk lies the halo, a vast, roughly spherical region that surrounds the disk and extends far into space. The halo is home to different populations of stars and, crucially, to most of the galaxy's dark matter. Understanding the halo is essential to understanding the Milky Way's true size. The stellar halo is made of ancient stars, some of the oldest in the galaxy. These stars formed billions of years ago, perhaps even before the disk fully assembled. They have different orbits than disk stars, moving in elongated ellipses that carry them far above and below the galactic plane. These halo stars are metal poor, meaning they contain very little of the heavy elements like iron and carbon. They formed from primordial gas that hadn't been enriched by supernovae yet, so their composition reflects the early universe more than modern stars do. By studying halo stars, astronomers can learn about the galaxy's early history. The halo also contains globular clusters, dense balls of hundreds of thousands of ancient stars. The Milky Way has about 150 known globular clusters, distributed throughout the halo. These clusters are beautiful objects, spherical concentrations of stars so tightly packed that near their centres, stars are separated by distances far smaller than the distances between stars in the disk. Globular clusters orbit the galaxy in the halo, following elliptical paths that take them from the inner regions out to vast distances and back. By measuring the positions and velocities of globular clusters, astronomers can map the halo structure and estimate its size. For a long time, the stellar halo was thought to extend about 100,000 light-years from the galactic center, roughly the same as the disk's diameter. But observations were difficult because halo stars are sparse. Unlike the disk, where stars are relatively close together, the halo has very low stellar density. Stars are separated by vast distances, making them hard to find and study. Dark matter is one of the great mysteries of modern astrophysics. We don't know what it's made of. It's not ordinary atoms or molecules. It doesn't interact with light. It passes through normal matter almost without interaction. Yet it makes up about 85% of the matter in the universe and dominates the mass of galaxies. In the Milky Way, the dark matter forms a roughly spherical halo that extends far beyond the visible stars. Estimating its size is challenging because we can't see dark matter directly. Instead, we infer its presence and distribution from the motions of objects that do emit light. By measuring how far stars and gas orbit at different distances from the Galactic Center, astronomers can calculate how much mass is present inside those orbits. The result is a rotation curve, a graph showing orbital velocity versus distance. If the Milky Way's mass were concentrated in the disk, the rotation curve would fall off at large distances, just like planets in the solar system orbit more slowly the farther they are from the Sun. But the Milky Way's rotation curve stays flat or even rises slightly at large distances, indicating that mass continues to increase with radius even where there are few visible stars. This is the signature of dark matter. The dark matter halo must extend well beyond the disk, adding mass at large radii and keeping the rotation curve flat. How far does the dark matter halo extend? This is one of the key questions about the Milky Way's size. Different studies give different answers, depending on the techniques used and the assumptions made. Some estimates suggest the halo extends to about 300,000 light-years. Others propose even larger sizes, perhaps 500,000 to 600,000 light-years. Recent measurements using satellite galaxies, small galaxies orbiting the Milky Way, suggest the dark matter halo might extend to about 1 million light-years from the Galactic Center. That would make the total diameter of the Milky Way's gravitational influence about 2 million light-years, an enormous increase from the old 100,000 light-year estimate for the disk. At these distances, we're reaching the edge of the Milky Way's gravitational dominance. Beyond about 1 million light-years, the gravity of the Andromeda galaxy, our nearest large galactic neighbour, becomes comparable to the Milky Way's. This region between the two galaxies is sometimes called the neutral zone, where neither galaxy's gravity clearly dominates. The halo, both stellar and dark matter, is crucial to understanding the Milky Way's true size. When we ask how big the galaxy is, we're really asking about this extended halo, because that's where most of the mass resides and where the galaxy's gravitational influence extends farthest. Discovering the halo's extent has been one of the major achievements of 21st century astronomy, made possible by surveys that have mapped millions of stars and by theoretical models that have helped us interpret the observations. We now know that the Milky Way is vastly larger than the disk alone, a giant cosmic structure whose true boundaries lie far beyond what our eyes can see. One of the great challenges in determining the Milky Way's size is measuring things we can't see directly. Dark matter, distant halo stars, the outer reaches of the disk, all push the limits of observation. Let's explore the clever techniques astronomers have developed to measure the invisible. Parallax is the oldest and most direct method of measuring stellar distances, but it only works for relatively nearby stars. As Earth orbits the Sun, nearby stars appear to shift position slightly relative to more distant background stars. By measuring this shift, called parallax, astronomers can calculate the star's distance using simple geometry. For centuries, parallax was limited to stars within a few hundred light-years. Ground-based telescopes couldn't measure the tiny angular shifts of more distant stars, but space-based missions have revolutionized parallax measurements. The Hipparcos satellite, launched in 1989, measured parallaxes for over 100,000 stars out to about 1,000 light-years. Then came Gaia, a European Space Agency mission launched in 2013. Gaia is mapping the positions, motions and distances of over 1 billion stars, about 1% of the Milky Way's total stellar population. Its measurements are extraordinarily precise, allowing parallax distances to be calculated for stars tens of thousands of light-years away. Cepheids can be detected in nearby galaxies, making them useful for measuring distances across millions of light-years. But within the Milky Way, dust obscures many Cepheids. making them harder to use for mapping our own galaxy. Aurillary stars are another type of variable star, older and less luminous than Cepheids. They're common in globular clusters and the halo, making them useful for mapping those regions. By measuring distances to aurillary stars and globular clusters, astronomers can map the halo's structure. For the dark matter halo, direct distance measurements aren't possible because dark matter doesn't emit light. Instead, astronomers use dynamics, the study of motion. By measuring how objects move under the influence of gravity, they can infer the distribution of mass, including dark matter. The rotation curve is one key tool. By measuring the velocities of stars and gas at different distances from the galactic center, astronomers can determine how much mass is enclosed within each radius. The rotation curve of the Milky Way stays flat out to at least 50,000 light-years, indicating the presence of dark matter at those distances. Beyond the disk, satellite galaxies provide crucial information. The Milky Way has about 60 known satellite galaxies, small galaxies orbiting our own. The large and small Magellanic Clouds are the most famous, visible in the southern hemisphere as cloud-like patches. But there are many others, most discovered in recent decades through deep surveys. By measuring the positions and velocities of these satellite galaxies, astronomers can estimate the Milky Way's total mass and the extent of its dark matter halo. The satellites orbit under the influence of the Milky Way's gravity, so their motions reveal the gravitational field and thus the mass distribution. The satellite galaxies are distributed over a vast volume, some orbiting close to the disk, others at distances of several 100,000 light-years. The most distant confirmed satellite is Crater 2, about 400,000 light-years away. Its orbit provides information about the dark matter halo at that distance. Computer simulations also play a role. Astronomers create models of galaxy formation and evolution, running simulations that start from the early universe and follow how dark matter halos form, how gas cools and forms stars, how galaxies merge and evolve. By comparing simulations to observations, they can constrain the Milky Way's properties, including the size of its dark matter halo. These simulations suggest that the Milky Way's dark matter halo might extend to a virial radius, the distance where the halo's density drops to about 200 times the average density of the universe. For the Milky Way, this virial radius is estimated at about 300,000 to 400,000 light-years. But there's uncertainty in all these measurements. Different techniques give somewhat different answers. Different assumptions in simulations lead to different halo sizes. The true size of the Milky Way's dark matter halo remains an active area of research. What we can say with confidence is that the Milky Way's gravitational influence extends at least several 100,000 light-years, and possibly close to 1 million light-years. This makes the galaxy far larger than the disk alone, a vast cosmic structure dominated by invisible dark matter. Measuring the invisible requires patience, ingenuity, and the combination of many different observations and techniques. It's detective work on a cosmic scale, piecing together clues to build a picture of something we can never see directly. But slowly, carefully, astronomers are mapping the Milky Way's full extent, revealing a galaxy much larger and more massive than earlier generations imagined. In the past decade, a series of new measurements has dramatically changed our understanding of the Milky Way's size. These discoveries, made possible by new telescopes and surveys, have shown that our galaxy is significantly larger than we thought. Let's explore these breakthrough findings. One of the most important discoveries came from mapping the outer disk. The Sloan Digital Sky Survey, or SDSS, has been systematically photographing the sky since 2000, creating a detailed map of millions of galaxies and stars. Within that data, astronomers found evidence of the disk extending much farther than expected. By analysing the distribution of certain types of stars, particularly M giants, cool red stars that are bright enough to be detected at great distances, researchers traced the disk out to about 80,000 light-years from the Galactic Center. This was significantly farther than the old 50,000 light-year estimate for the disk's edge. But it wasn't just that the disk extended farther. The structure itself was different than expected. The outer disk appeared to be warped, bent like the brim of a hat that's been sat on. This warping had been suspected from observations of hydrogen gas, but seeing it in the stellar distribution confirmed that the entire outer disk is warped. The warp might be caused by gravitational interactions with the large and small Magellanic Clouds, the Milky Way's largest satellite galaxies. As they orbit our galaxy, their gravity tugs on the outer disk, bending it out of the flat plane. Computer simulations support this idea, showing that passing satellite galaxies can create exactly this kind of warping. Another major discovery involved the stellar halo. The SDSS and other surveys found streams of stars extending to enormous distances, over 200,000 light-years from the Galactic Center. These streams are the remnants of smaller galaxies and globular clusters that have been torn apart by the Milky Way's tidal forces. One particularly important stream is the Sagittarius stream, debris from the Sagittarius dwarf elliptical galaxy, a small galaxy currently being destroyed by its orbit around the Milky Way. The stream wraps around the entire galaxy, visible both above and below the disk, providing a tracer of the Milky Way's gravitational field at large distances. By mapping these streams and measuring their motions, astronomers can constrain the distribution of dark matter. The stream's shapes and velocities depend on the Milky Way's gravitational potential, which is dominated by dark matter at large distances. The data suggests the dark matter halo is more extended than previous models predicted. Perhaps the most significant breakthrough came from measuring the Milky Way's total mass. This is closely related to size because the dark matter halo's extent depends on the total mass. Several recent studies have combined data from Gaia, which measured the positions and velocities of stars and globular clusters, with measurements of satellite galaxy motions. In 2019, a team of astronomers published results suggesting the Milky Way's total mass, including dark matter, is about 1.5 trillion solar masses, significantly more massive than previous estimates. This higher mass implies a more extended dark matter halo. This suggests the Milky Way's effective size, its gravitational domain, extends to about 1 million light-years from the Galactic Center, making the total diameter about 2 million light-years. This is an enormous region, 20 times larger than the visible disk. Recent observations of satellite galaxies support this picture. The most distant satellites, orbiting at 400,000 to 500,000 light-years, are still clearly bound to the Milky Way, their velocities indicating they're orbiting rather than passing by. This confirms the dark matter halo extends at least that far. There's also evidence from high-velocity clouds, clouds of hydrogen gas moving at speeds different from the disk's rotation. Some of these clouds are falling into the Milky Way from the halo, possibly material left over from the galaxy's formation, or gas stripped from satellite galaxies. Their distribution and motions provide additional information about the halo's extent. All these measurements point to the same conclusion. The Milky Way is much larger than we thought. The disk is bigger, extending to perhaps 80,000 to 100,000 light-years from the center. The stellar halo reaches past 200,000 light-years. The dark matter halo likely extends to 300,000 to 500,000 light-years, possibly farther. When we say we finally know how big the Milky Way is, we're recognizing this new understanding. The galaxy isn't the 100,000 light-year diameter disk of older textbooks. It's a complex extended structure with multiple components reaching to vastly different distances, dominated by a dark matter halo that extends far into space. This new picture has emerged from decades of patient observation, from surveys that have mapped millions of stars, from space missions that have measured distances with unprecedented precision, and from theoretical work that has helped us interpret the data. It's one of the great achievements of 21st century astronomy, measuring our cosmic home from the inside and revealing its true magnificent scale. At the heart of the Milky Way, 26,000 light-years from our solar system, lies the Galactic Center, a crowded, energetic region unlike anywhere else in the galaxy. Understanding the centre is crucial to understanding the galaxy as a whole, because what happens there influences the entire structure. The galactic centre is hidden from our view in visible light. Vast clouds of dust block our direct sight, absorbing and scattering starlight. If we could see through the dust, the night sky would be dominated by the brilliant glow of billions of stars packed tightly together in the central bulge. But the dust intervenes, leaving only the faint band of the Milky Way visible to our eyes. Fortunately, infrared and radio waves penetrate dust much better than visible light. Infrared telescopes can peer into the heart of the galaxy, revealing dense clusters of stars, glowing clouds of gas, and energetic phenomena. Radio telescopes detect emissions from molecules and from high-energy processes that visible light cannot show. What these observations reveal is astonishing. The galactic centre hosts a supermassive black hole, an object containing about 4 million times the Sun's mass compressed into a region smaller than our solar system. This black hole, called Sagittarius A star, is the gravitational anchor around which the entire galaxy rotates. There's also a lot of gas and dust near the centre. Molecular clouds, stellar winds from massive stars, and supernova remnants create a complex dynamic medium. X-ray observations reveal hot gas at millions of degrees, heated by supernova explosions and by shock waves from stellar winds colliding. The galactic centre influences the entire galaxy through its gravitational field and through outflows of energy and matter. While Sagittarius A star is relatively quiet now, there's evidence it was more active in the past, perhaps accreting material and ejecting powerful jets or winds that affected the surrounding gas. Some galaxies have much more active central black holes, so-called active galactic nuclei, wherein falling matter creates brilliant emissions visible across the universe. Our black hole is dormant by comparison, but even in its quiet state, it dominates the central region. The bulge, the concentration of stars surrounding the galactic centre, extends about 10,000 light-years from the centre. It contains mostly old stars, formed billions of years ago when the galaxy was young. These stars have random orbits, moving in all directions rather than the organised rotation of the disk. Recent observations suggest the bulge has a complex structure. It's not perfectly spherical, but somewhat elongated, forming a bar-like structure oriented at an angle to our line of sight. This bar might help channel gas from the disk toward the centre, influencing star formation and black hole feeding. The galactic centre region, despite being distant and obscured, has been intensively studied because it offers a unique laboratory for extreme physics. Nowhere else in the galaxy can we study stars orbiting so close to a supermassive black hole, test general relativity in such strong gravitational fields, or observe such extreme stellar densities. Understanding the centre is also crucial for understanding the galaxy's overall mass distribution. The central black hole, while massive, is only a tiny fraction of the galaxy's total mass. But the bulge contains significant mass, and its gravitational influence extends throughout the galaxy. As we think about how big the Milky Way is, the galactic centre provides the reference point. Distances in the galaxy are often measured from the centre, and the centre's gravitational field organises the rotation of the disk and the orbits of halo objects. The centre is where it all began, where the galaxy first formed and where its deepest gravitational well resides. One of the most beautiful features of spiral galaxies like the Milky Way is the spiral arms, graceful curves of stars and glowing gas that wind outward from the centre. Understanding the spiral structure is important for understanding the galaxy's size and shape, though mapping it from inside has proven challenging. When we look at other spiral galaxies, we see clearly defined arms, often two or more major arms with smaller arm segments between them. The arms are bright because they contain young, hot blue stars and glowing nebulae, regions where new stars are actively forming. These features light up the spiral pattern, making it visible across millions of light-years. But mapping the Milky Way's spiral structure is much harder because we're embedded in the disk. We see stars in all directions, and it's difficult to determine which stars belong to which arm. Dust obscures our view across the disk, preventing us from seeing the full pattern. It's like trying to understand the layout of a city while standing at street level, with buildings blocking your view. Despite these challenges, astronomers have made significant progress. By mapping the positions of young stars, star-forming regions and molecular clouds, they've pieced together the Milky Way's spiral pattern. The galaxy has 4 major arms: the Perseus arm, the Scutum Centaurus arm, the Sagittarius arm, and the Norma arm. Our Sun is located in a smaller structure called the Orion spur or local arm, a partial arm between the Perseus and Sagittarius arms. This positioning gives us a relatively clear view of both neighbouring arms, helping astronomers map the structure. The spiral arms are not material structures in the sense that the same stars always remain in them. Instead, they're density waves, regions where stars and gas bunch up temporarily. Stars orbit the galaxy at different speeds depending on their distance from the centre, and as they move, they pass through spiral arms, slow down slightly due to the increased gravity, then speed up as they leave. It's similar to traffic on a highway. Cars enter a congested zone, slow down, bunch together, then accelerate once through. The pattern of congestion persists even though individual cars move through it. Similarly, spiral arms persist as patterns even though stars constantly move through them. This wave pattern is maintained by the galaxy's rotation and gravitational dynamics. Computer simulations show that spiral density waves are natural features of rotating disk galaxies, arising from gravitational instabilities and persisting for billions of years. The spiral arms are where most star formation occurs. As gas and dust enter a spiral arm, the density wave compresses them, triggering gravitational collapse. Massive clouds fragment into thousands of smaller clumps, each collapsing to form a star. The most massive stars form quickly and shine brilliantly, lighting up the spiral arm. There's also evidence that the spiral pattern might change over time. Interactions with satellite galaxies, like the Large Magellanic Cloud, could perturb the disk and alter the spiral arms. Some simulations suggest the Magellanic Cloud's gravity has created a new spiral arm, or enhanced existing arms in the outer disk. The spiral arms are not evenly spaced or perfectly symmetrical. They have different lengths, different brightnesses, different pitches, how tightly they wind. This asymmetry provides clues about the galaxy's history, about past interactions and mergers that have shaped the disk. Understanding the spiral structure also helps us locate the Sun's position in the galaxy. By mapping the arms and determining which arm we're in, or between, astronomers can better determine our distance from the Galactic Center and our motion through the disk. The current best estimate places us about 26,000 light-years from the center, in the Orion spur, moving at about 220 km per second around the center. We're slightly above the midplane of the disk, about 70 light-years above, though this varies as we oscillate up and down through the disk over tens of millions of years. The spiral arms, then, are a key component of the disk's structure, organising star formation, creating beautiful patterns, and helping us map our position within the galaxy. They're part of what makes the Milky Way a grand-designed spiral galaxy, one of the more organised and symmetric spiral galaxies in the universe. The Milky Way doesn't exist in isolation. It's surrounded by a family of smaller satellite galaxies, objects orbiting our galaxy like moons orbit a planet. Understanding these satellites is crucial to understanding the Milky Way's size, because they trace the outer reaches of our galaxy's gravitational influence. The two most famous satellites are the Large and Small Magellanic Clouds, visible to the naked eye in the southern hemisphere. They appear as hazy patches of light, like detached pieces of the Milky Way. Ancient observers in the southern hemisphere knew about them, and they're named after Ferdinand Magellan, whose crew documented them during the first circumnavigation of Earth in the early 16th century. The Large Magellanic Cloud, or LMC, is about 160,000 light-years away, a relatively close neighbour in cosmic terms. It contains about 10 billion stars, making it perhaps 1/10 the mass of the Milky Way's disk. The Small Magellanic Cloud, or SMC, is slightly farther at about 200,000 light-years and contains a few billion stars. These galaxies are irregular in shape, lacking the organised disk of spiral galaxies or the smooth distribution of elliptical galaxies. They're called dwarf irregular galaxies, and they're actively forming stars. In fact, the LMC contains the Tarantula Nebula, one of the most active star-forming regions in our cosmic neighbourhood, a vast cloud of glowing gas where thousands of massive stars have recently formed. Beyond the Magellanic Clouds are dozens of smaller satellite galaxies. Most are dwarf spheroidal galaxies, small collections of old stars with little or no ongoing star formation. They're faint, difficult to detect, and most were discovered only in recent decades through systematic surveys. The Sagittarius dwarf elliptical galaxy is particularly interesting. It's only about 70,000 light-years from the Galactic Center, closer than the LMC, and it's currently being torn apart by the Milky Way's tidal forces. Streams of stars from Sagittarius wrap around the entire galaxy, providing one of the clearest examples of galactic cannibalism, the process by which large galaxies grow by consuming smaller ones. The satellite galaxies are distributed over a vast volume around the Milky Way. Some orbit close, within 100,000 light-years. Others are farther out, at 300,000 to 500,000 light-years. A few might be even more distant, at the very edge of the Milky Way's gravitational influence. These distant satellites are crucial for measuring the Milky Way's mass and the extent of its dark matter halo. By observing their positions and velocities, astronomers can calculate how much mass is required to keep them bound. The answer is always much more than the visible stars suggest, confirming the presence of a massive dark matter halo. The number of known satellite galaxies has grown dramatically in recent years. Before 2000, only about a dozen were known. Now we know of about 60, and there are probably more waiting to be discovered. They're extremely faint, with some containing only a few thousand stars, making them difficult to detect against the background of more distant galaxies and foreground stars. The discovery of so many faint satellites was initially surprising, because theoretical models predicted there should be hundreds of small dark matter halos orbiting the Milky Way. But we only see dozens of luminous satellites. This discrepancy, called the quote one, has been a puzzle for cosmologists. One explanation is that many small dark matter halos exist but never formed stars, remaining dark and invisible. Another is that the predictions were wrong, perhaps because feedback from supernovae prevents star formation in the smallest halos, or because the nature of dark matter is different than assumed. Recent discoveries have helped resolve this tension. We're finding more and more faint satellites, and theoretical work has refined the predictions. The number of observed satellites is now closer to theoretical expectations, suggesting our understanding is improving. The satellite galaxies also tell us about the Milky Way's history. Each satellite is a fossil, a relic of earlier epochs when galaxy formation was more chaotic. Some satellites might be remnants of larger galaxies that have been partially destroyed. Others might be pristine objects that have survived unchanged since the early universe. By studying the ages and compositions of stars in satellite galaxies, astronomers can learn about when they formed and how they've evolved. This provides a timeline of the Milky Way's growth, showing when different satellites were captured or formed. The satellite system extends the Milky Way's influence far into space. The most distant confirmed satellites are about 500,000 light-years away. Beyond that distance, the Andromeda galaxy's gravity becomes competitive, and objects might orbit Andromeda rather than the Milky Way, or they might be unbound, adrift in the space between galaxies. This swarm of satellites is part of what makes the Milky Way a giant. Not all galaxies have such extensive satellite systems. The fact that we do suggests the Milky Way has been effective at capturing smaller galaxies over cosmic history. growing through mergers and accretion. To truly appreciate the Milky Way's size, it helps to compare it to our nearest large galactic neighbour, the Andromeda Galaxy, also known as M31. This comparison provides context and perspective, showing where the Milky Way fits in the cosmic hierarchy of galaxies. Andromeda is the nearest large spiral galaxy to the Milky Way, about 2.5 million light-years away. On a dark, clear night, far from city lights, you can see it with the naked eye as a faint, fuzzy patch in the constellation Andromeda. Through a telescope, its spiral structure becomes visible, a beautiful disk tilted at an angle to our line of sight. For decades, astronomers thought Andromeda was significantly larger than the Milky Way. Estimates suggested Andromeda's disk was about 220,000 light-years across, more than twice the Milky Way's old 100,000 light-year diameter. Andromeda was considered the giant of our local group, the collection of about 100 galaxies bound together by gravity, with the Milky Way as a smaller sibling. But recent measurements have changed this picture. As we've discovered the Milky Way is larger than previously thought, estimates of Andromeda's size have also been refined. If the galaxies have similar masses, the merger will be more of a collision between equals rather than a large galaxy consuming a small one. The dynamics will be complex, with both galaxies being disrupted and reshaped. Eventually they'll merge into a single larger elliptical galaxy, sometimes called Milkomeda or Milkdromeda. Comparing the two galaxies' structures also reveals differences. Andromeda has a more prominent bulge, a larger central concentration of stars. It might have experienced more mergers in its past, building up its centre. The Milky Way has a smaller bar-shaped bulge, suggesting a different history. Andromeda also has more satellite galaxies than the Milky Way, at least in current catalogues, but this might be an observational bias. Andromeda's satellites are all at roughly the same distance from us, making them easier to detect than the Milky Way's satellites, which are spread across a range of distances and often hidden behind or confused with the Milky Way's disk and halo. Both galaxies are actively interacting with their satellites. Andromeda is shredding M32 and M110, two of its larger satellites. Pulling stars away through tidal forces, the Milky Way is doing the same to Sagittarius and possibly to the Magellanic Clouds. These ongoing interactions show that both galaxies are still growing, still accreting smaller galaxies. Galaxy evolution is an ongoing process, not something that happened only in the distant past. Both the Milky Way and Andromeda are larger now than they were 1 billion years ago, and they'll be larger still after they merge. The comparison with Andromeda puts the Milky Way's size in context. We're not living in the largest galaxy in the universe, far from it. There are giant elliptical galaxies containing trillions of solar masses and extending across hundreds of thousands or even millions of light-years. But among spiral galaxies, the Milky Way is one of the largest in our cosmic neighbourhood. This makes our galaxy somewhat special. Most galaxies in the universe are dwarfs, small collections of stars with masses a tiny fraction of the Milky Way's. Large spirals like ours and Andromeda are relatively rare. Being part of such a galaxy means we live in a rich, complex environment with ongoing star formation, interesting dynamics, and a long, eventful history. The Milky Way and Andromeda, as the two giants of the local group, dominate the gravitational landscape. Smaller galaxies orbit them, and the two giants are slowly approaching each other. When they merge, they'll create one of the largest galaxies in this region of the universe, a massive elliptical that will be the remnant of both proud spirals. Until then, we can appreciate living in our time, when the Milky Way is a beautiful spiral, actively forming stars, evolving through interactions with satellites, and large enough to contain hundreds of billions of stars and worlds. We've measured it, we know its size, and we can marvel at the fact that this vast structure is our cosmic home. Where does the Milky Way end and intergalactic space begin? This question might seem simple, but as we've learned, it has no clear answer. The galaxy doesn't have a sharp edge. Instead, it gradually fades into the surrounding universe. Let's think about what defines the boundary. and what exists at the edge. For the disk, the edge is where stellar density drops to some arbitrary threshold. Different studies use different thresholds, leading to different edge locations. You might define the edge as the point where star density drops to 1% of the value in the solar neighbourhood, or you might use a different percentage. Each choice gives a different radius. Recent studies tracking individual stars have found disk stars at distances of 70,000 to 80,000 light-years from the Galactic Center, farther than the old 50,000 light-year edge. But these outer disk stars are sparse. Between them are vast stretches of space with no stars at all, or at least none we've detected. There's also the question of the disk's thickness. Near the Sun, the thin disk is about 1,000 light-years thick, but in the outer galaxy, the disk appears to flare, becoming thicker. At 60,000 light-years from the centre, the disk might be several thousand light-years thick. This thickening might be caused by gravitational interactions with the Magellanic Clouds, or by the disk's own internal dynamics. For the stellar halo, the boundary is even less clear. Halo stars have been found over 200,000 light-years from the Galactic Center, but they're extremely rare at those distances. The halo's stellar density falls off roughly as 1 over distance cubed, meaning it drops very steeply. At large distances, you might go thousands of light-years between halo stars. There's also the question of escape stars. Some stars have been ejected from the Milky Way by gravitational interactions, achieving velocities high enough to escape the galaxy's gravity. These hypervelocity stars can travel hundreds of thousands or even millions of light-years from the galaxy. Several hypervelocity stars have been discovered, most of them likely ejected from the Galactic Center through interactions with the supermassive black hole. When a binary star system passes close to the black hole, one star can be captured into a tight orbit while the other is flung away at tremendous speed, thousands of kilometers per second. These escaped stars are no longer part of the Milky Way in a meaningful sense. They're escapees, former residents now travelling through intergalactic space, but they were born in the Milky Way, and they carry with them chemical signatures of their origin. The space between the Milky Way and neighbouring galaxies is not completely empty. It contains intergalactic gas, very diffuse hydrogen and helium left over from the Big Bang, or expelled from galaxies by stellar winds and supernovae. This gas has extremely low density, perhaps 1 particle per cubic metre, compared to a few particles per cubic centimetre in the galactic disk. High-velocity clouds, clouds of hydrogen gas falling into the Milky Way or orbiting in the halo, might represent material at the boundary. Some clouds could be primordial gas accreting onto the galaxy for the first time. Others might be gas torn from satellite galaxies. Their distribution and velocities provide clues about where the galaxy's influence ends. The Magellanic Stream, the trail of gas from the Magellanic Clouds, extends across much of the southern sky. Parts of it are over 1 million light-years long, reaching from the Magellanic Cloud's current position back along their orbit. This stream is technically outside the Milky Way's main body, but within its sphere of influence, captured by our galaxy's gravity. When we talk about the Milky Way being 1 million or 2 million light-years across, we're including this sphere of influence, the region where the Milky Way's gravity dominates. It's the largest meaningful definition of the galaxy's size, encompassing everything bound to our gravitational potential. But even this has ambiguity. Objects at these distances might be barely bound, moving so slowly relative to the galaxy that a small change in velocity would let them escape. Or they might be on elongated orbits that carry them far beyond 1 million light-years before falling back. The edge of the galaxy, then, is not a line but a transition zone, a gradual fading from the dense, star-filled disk and bulge through the sparse halo to the near emptiness of intergalactic space. It's a gradient, not a boundary. This ambiguity is actually common in astronomy. Few cosmic structures have sharp edges. Stars fade into planetary nebulae and eventually white dwarfs. Planetary atmospheres thin into space. Galactic clusters gradually merge with the cosmic web. Nature favours gradual transitions over sharp boundaries. So when we say the Milky Way is a certain size, we're always implicitly defining what we mean by the edge. Different definitions give different sizes, from the 100,000 light-year disk to the million light-year sphere of influence. All are valid, each describing a different aspect of our galaxy's extent. The Milky Way exists within a larger structure called the local group, a collection of about 100 galaxies bound together by gravity. Understanding the local group provides context for the Milky Way's size and shows how our galaxy fits into the larger cosmic hierarchy. The local group is dominated by two giant spirals, the Milky Way and Andromeda. Together, they contain most of the mass and most of the stars in the group. The third largest member is the Triangulum Galaxy, or M33, another spiral with about 50 billion stars, roughly 1/5 the mass of the Milky Way. Beyond these three, all other members are dwarf galaxies. The local group spans about 10 million light-years across, with the Milky Way and Andromeda at opposite ends, and smaller galaxies distributed throughout the volume. Some dwarf galaxies orbit the Milky Way, some orbit Andromeda, and some orbit in the space between, perhaps not firmly bound to either giant. This distribution is not random. It reflects the history of the local group's formation and evolution. Computer simulations suggest the local group formed from two concentrations of dark matter that attracted surrounding galaxies. Over billions of years, these concentrations became the Milky Way and Andromeda, with each accumulating satellites. The dwarf galaxies are diverse. Some, like the Magellanic Clouds, are irregular and actively forming stars. Others, like the Fornax and Sculptor dwarf spheroidals, contain only old stars and show no recent star formation. These differences reflect variations in their histories, their masses, and their interactions with the larger galaxies. Dwarf galaxies are important for understanding galaxy formation because they're thought to be the building blocks from which larger galaxies grew. In hierarchical models of structure formation, small dark matter halos form first, then merge and accrete to build progressively larger halos and galaxies. Dwarf galaxies are the modern descendants of these early building blocks. By studying dwarf galaxies in the local group, astronomers can test models of galaxy formation on small scales. They can examine how stars form in low-mass systems, how supernovae affect small galaxies, and how interactions with larger galaxies transform dwarfs over time. The Milky Way satellite system is particularly well studied because it's nearby. We can resolve individual stars in these galaxies, measure their ages and compositions, and reconstruct their star formation histories. This level of detail is impossible for satellite systems around distant galaxies. One surprising discovery is that many Milky Way satellites appear to lie in a plane, rather than being randomly distributed in 3 dimensions. This plane is called the satellite plane or disk of satellites. Its existence is puzzling because cosmological simulations predict satellites should be randomly distributed. Not aligned. Several explanations have been proposed. Maybe the satellites formed from a single large structure that broke apart. Maybe they were captured from a nearby galaxy group. Maybe it's a statistical fluke, and with more satellites discovered, the plane will disappear. Or maybe there's something wrong with our models of dark matter or galaxy formation. The smaller galaxies in the local group will also be affected. Some might be pulled into the merger, adding their stars to the mix. Others might be flung outward, ejected into intergalactic space by the gravitational chaos. A few might survive intact, becoming satellites of the merged galaxy. After the merger, the new galaxy will be an elliptical, a different type of galaxy with no spiral structure. Little ongoing star formation and a smooth distribution of stars. It will be one of the largest galaxies in this region of the universe, a testament to the growth that occurs through mergers. But this is billions of years in the future. For now, the local group consists of 3 spiral galaxies and dozens of dwarfs, a gravitationally bound system slowly evolving as galaxies orbit, interact, and occasionally merge. The local group's size, about 10 million light-years, provides a natural comparison point for the Milky Way. The galaxy is about 1/10 to 1/5 the diameter of the local group, depending on how you measure. This makes it a significant component of the group but not the dominant structure. Thinking about the local group helps us appreciate the Milky Way's place in the universe. We're part of a small cluster of galaxies, bound together by gravity, isolated from other galaxy groups by millions of light years of nearly empty space. Our group is one of countless such groups throughout the universe, each containing a few large galaxies and many small ones. This hierarchical structure, small groups merging into larger clusters, clusters forming superclusters, superclusters arranged in vast filaments and walls surrounding cosmic voids, is one of the fundamental patterns of the universe. The local group is our place in this hierarchy, and the Milky Way is our place within the group. Let's pause and reflect on the remarkable fact that we can measure the size of the Milky Way at all. We're stuck on a small planet, unable to leave even our solar system, looking out at a galaxy that surrounds us. Yet we've determined its size to within reasonable uncertainty. How is this possible? The answer lies in the scientific method, the patient accumulation of observations, the development of theoretical frameworks, and the interplay between theory and experiment. Over centuries, astronomers have built up techniques and knowledge that allow us to infer things we cannot directly observe. Distance measurement is fundamental. Almost everything we know about the Milky Way's size depends on measuring distances to stars, gas clouds, and other objects. The ladder of cosmic distances, with each rung calibrated using the previous one, extends from Earth to the edge of the observable universe. The first rung is parallax, the gold standard for nearby stars. By measuring the tiny shift in a star's position as Earth orbits the Sun, we can calculate its distance using basic trigonometry. This has been done since the 19th century, but modern missions like Hipparcos and Gaia have revolutionized the precision and range. Gaia, in particular, has been transformative. It's measuring positions and motions for over 1 billion stars with incredible precision, some good to within a few percent even for stars thousands of light years away. This dataset is unprecedented, allowing detailed mapping of the disk and halo. For more distant objects beyond parallax range, we use standard candles. The key is finding objects whose intrinsic brightness we can determine independently of their distance. Then, by measuring how bright they appear, we can calculate how far away they must be to appear that dim. Cepheid variable stars are classic standard candles. Their pulsation period relates to their luminosity through a period-luminosity relation discovered by Henrietta Leavitt in the early 20th century. This relationship has been calibrated using nearby Cepheids, with parallax distances, then extended to Cepheids in other galaxies. Theoretical models also play a crucial role. Simulations of galaxy formation, starting from the early universe and evolving forward in time, predict what we should see. By comparing simulations to observations, we can test our understanding and refine models. These simulations require supercomputers and incorporate complex physics, gravity, hydrodynamics, star formation, supernova feedback, black hole growth, chemical enrichment. They're simplified compared to reality but capture the essential processes. Agreement between simulations and observations gives confidence in our understanding. Statistical methods are important too. With large data sets from surveys, astronomers use statistical techniques to identify patterns, find outliers, estimate population properties. Machine learning algorithms help classify millions of stars, search for rare objects, identify subtle trends. The whole enterprise is collaborative. Thousands of astronomers worldwide contribute observations, develop theories, build instruments, analyze data. Results are published in journals where others can scrutinize methods and reproduce findings. Knowledge accumulates through this collective effort. There's also serendipity. Sometimes discoveries come from unexpected observations. The Magellanic Stream was discovered accidentally in radio observations. stellar streams from disrupted satellites emerge from surveys designed for other purposes. Keeping an open mind and being alert to anomalies often leads to new insights. Technological advances drive progress. Each new telescope, each improved detector, each faster computer opens possibilities. The Hubble Space Telescope revolutionized extragalactic astronomy. Gaia is revolutionizing our understanding of the Milky Way. Future instruments will bring new discoveries. But underlying all this technology and technique is human curiosity, the desire to understand where we are and what surrounds us. That curiosity drives people to spend careers measuring stellar positions, analysing galactic orbits, building computer models, pushing the boundaries of knowledge. The fact that we can determine the Milky Way's size from our position inside it is a testament to human ingenuity. We can't step outside to look. We can't send a probe to measure directly, but through careful observation, clever reasoning and patient work we can map our cosmic home. This is science at its best, taking in complete information, using logic and mathematics to infer what we cannot directly see, testing predictions against new observations, refining understanding through iterations of hypothesis and experiment. It's how we know what we know. And what we know now is that the Milky Way is far larger than earlier generations imagined. It's a giant among spirals, extending across hundreds of thousands of light years in its disk, surrounded by a halo reaching into the millions of light years. We live in a vast, magnificent structure, and we've measured it from the inside. Perhaps the most profound aspect of understanding the Milky Way's size is recognizing that most of it is invisible. The dark matter halo, which extends much farther than the visible stars, contains most of the galaxy's mass. Let's think deeply about what this means. Dark matter is one of the great mysteries of modern science. We know it exists through its gravitational effects, but we don't know what it's made of. It's not atoms or molecules, not any form of ordinary matter. It doesn't emit, absorb, or reflect light. It passes through normal matter with almost no interaction. Yet it's 5 times more abundant than ordinary matter in the universe. In the Milky Way, dark matter dominates at large distances from the centre. Within the solar orbit, about 26,000 light-years from the centre, there's roughly equal amounts of dark matter and ordinary matter. But beyond that, dark matter becomes increasingly dominant. In the outer halo, dark matter might outweigh ordinary matter by factors of 10 to 1 or more. This means that most of the Milky Way's extent is dark matter. The visible disk and stellar halo, impressive as they are just the illuminated centre of a much larger dark structure. It's like seeing the lights of a city at night and realising the city extends far beyond the illuminated areas into dark suburbs and countryside. The dark matter distribution is roughly spherical, or perhaps slightly ellipsoidal surrounding the disk. It's smooth on large scales, but probably clumpy on small scales, containing subhalos, smaller concentrations of dark matter that didn't form stars or formed dwarf galaxies. This dark matter halo formed first in the early universe. Before the disk, dark matter started collapsing under its own gravity while ordinary matter was still too hot and diffuse to clump. As dark matter concentrated, it created gravitational wells that ordinary matter fell into, cooling and forming stars. The disk formed later. As gas cooled and settled into a rotating plane within the dark matter halo. The rotation of the disk is supported by both its own angular momentum and by the gravitational potential of the dark matter halo. Without dark matter, the disk might not be stable. Stars would have different orbits, possibly disrupting the spiral structure. Understanding dark matter's role in galaxy formation is one of the major goals of cosmology. Simulations show that dark matter halos provide the scaffolding for galaxies. Ordinary matter fills in these halos, but the halo's properties, its mass, concentration, and merger history strongly influence the resulting galaxy. The Milky Way's dark matter halo mass is estimated at about 1 trillion solar masses, much larger than the visible mass of stars and gas. which totals perhaps 100 billion to 200 billion solar masses. This means dark matter outweighs ordinary matter by a factor of 5 to 10 in our galaxy. This dark matter didn't form stars because dark matter can't cool and concentrate the way ordinary matter can. Ordinary matter can radiate energy through electromagnetic processes, allowing it to lose energy, collapse, and form dense objects like stars. Dark matter has no such mechanism. It remains diffuse, forming halos but not compact objects. There are ongoing searches for dark matter particles. Experiments deep underground look for rare interactions between dark matter and ordinary matter. Particle accelerators search for dark matter creation in high-energy collisions. Space telescopes look for gamma rays from dark matter annihilation. So far, no definitive detection, but the search continues. Some alternative theories propose modifying gravity instead of invoking dark matter. Modified Newtonian dynamics, or MOND, and related ideas suggest gravity behaves differently at low accelerations, explaining galactic rotation curves without dark matter. But these theories have difficulty explaining other observations, like galaxy clusters and the cosmic microwave background, where dark matter models work well. It's humbling but also empowering. Humbling because it shows how much we don't know, how limited our direct perception is. Empowering because it shows we can figure things out anyway, using reason and observation to infer what we cannot directly detect. Dark matter also connects the Milky Way to the broader universe. All galaxies have dark matter halos. The large-scale structure of the universe, the cosmic web of filaments and voids, is shaped primarily by dark matter. Understanding dark matter in the Milky Way helps us understand galaxy formation everywhere. As we contemplate the galaxy's size, we must remember that size isn't just about light years. It's about mass, gravity, structure. The Milky Way is large because its dark matter halo is large. That halo is invisible, but it's real, and it defines our galaxy's true extent. Let's zoom out and think about where the Milky Way fits in the grand scheme of the universe. Understanding its size means understanding whether it's typical or unusual, large or small compared to other galaxies. In the universe, galaxies range enormously in size and mass. The smallest dwarf galaxies contain only thousands or millions of stars and might span just a few hundred light years. The largest giant ellipticals contain trillions of stars and can extend across several million light years. The Milky Way, with its 100 billion to few hundred billion stars and its extended dark matter halo, is definitely in the large category. It's not the largest galaxy in the universe, far from it, but it's larger than most. Surveys show that the majority of galaxies are dwarfs, with only a small fraction being giants like ours. Among spiral galaxies specifically, the Milky Way is one of the largest in the local universe. Most spirals are smaller, with fewer stars and less mass. The Andromeda galaxy is similar in size, perhaps slightly larger in some measurements. A few other local spirals, like M81 and NGC 253, are comparable, but these are the exceptions rather than the rule. This makes Earth's location somewhat special. We happen to live in one of the larger spiral galaxies in our cosmic neighbourhood. If life arose in a random galaxy, it would more likely be in a dwarf. But there are reasons to think large galaxies might be more favourable for life. Large galaxies have ongoing star formation for billions of years, continuously enriching their gas with heavy elements. This provides the raw materials, carbon, oxygen, nitrogen, silicon, and iron needed for planets and life. Dwarf galaxies often have short bursts of star formation followed by quiescence, potentially limiting their habitability. In terms of mass, though, the picture is different. Because giant galaxies are so much more massive, they contribute disproportionately to the total stellar mass in the universe. A large fraction of all stars reside in giant galaxies, even though giant galaxies are rare by count. The Milky Way's size has evolved over time. It started small, from the collapse of a dark matter halo in the early universe. Over billions of years, it grew through star formation and through mergers with smaller galaxies. It's larger now than it was 10 billion years ago, and it will be larger still after merging with Andromeda. This growth through mergers is a key process in galaxy evolution. Simulations show that large galaxies like the Milky Way have merged with dozens or hundreds of smaller galaxies over their lifetimes. Each merger adds mass and sometimes triggers bursts of star formation. Evidence for these past mergers can be seen in the halo. Stellar streams, like the Sagittarius stream, are remnants of disrupted satellites. The ages and compositions of halo stars reflect multiple populations, each from a different accreted galaxy. By studying the halo, astronomers can reconstruct the Milky Way's merger history. Compared to the universe's larger structures, the Milky Way is tiny. Galaxy clusters contain hundreds or thousands of galaxies in a region tens of millions of light-years across. Superclusters contain multiple clusters and span hundreds of millions of light-years. The cosmic web, the largest pattern, has filaments stretching across billions of light-years. But compared to individual galaxies, the Milky Way is large. It's a significant structure, one of the giants, with a complex history and a rich environment for star and planet formation. This cosmic context helps us appreciate what it means to have measured the Milky Way's size. We're not just measuring some arbitrary object. We're measuring one of the largest galaxies in our region of space, a structure that has been growing for over 13 billion years, that contains the matter from hundreds of smaller galaxies, that spans distances almost incomprehensible to human scales. And we're doing it from the inside, from a planet orbiting an ordinary star in an ordinary spiral arm, using light and gravity and mathematics to map the extent of our cosmic home. It's one of the great achievements of human civilization, and it's worth pausing to appreciate just how remarkable it is. Knowing the Milky Way's size isn't just about satisfying curiosity. It tells us important things about the galaxy's history, its future, and its role in the universe. Let's think about what we learn from these measurements. The size of the disk, now measured at about 170,000 to 200,000 light-years across, including the warped outer regions, tells us about the galaxy's mass and angular momentum. A larger disk implies more material settled into rotational equilibrium, which in turn tells us about the collapse and settling of gas in the early galaxy. The fact that the disk extends so far suggests it's been able to accrete gas over billions of years without major disruptions. If the Milky Way had undergone a major merger recently, say in the past few billion years, the disk would likely be disturbed, heated, and thickened. The relatively thin, extended disk we observe suggests the last major merger was long ago. The size and structure of the halo, with its multiple stellar streams and extended dark matter distribution, tells us about the mergers that have occurred. Each stream represents a disrupted satellite galaxy. By counting streams and estimating their masses, astronomers can estimate how much mass the Milky Way has accreted through mergers. Current estimates suggest the Milky Way has merged with about 5 to 10 dwarf galaxies, with masses of about 1 billion solar masses or more over the past 10 billion years. Hundreds of smaller mergers, involving even tinier galaxies, have also occurred. All this accretion has contributed to the halo's extent and structure. The dark matter halo's size, estimated at 300,000 to 1 million light-years, tells us about the Milky Way's total mass. A more extended halo requires more mass to remain bound. Recent measurements suggesting the halo extends to about 1 million light-years imply a total mass of around 1 to 2 trillion solar masses. This mass estimate affects our understanding of the galaxy's future. More massive galaxies have stronger gravity and can capture satellites from greater distances. The Milky Way's substantial mass means it has been effective at gathering smaller galaxies over cosmic history and will continue to do so. The size of the Milky Way also affects estimates of how many stars it contains. If the disk is larger than thought, it probably contains more stars. Current estimates range from 100 billion to 400 billion stars, with the uncertainty driven partly by uncertainty in the galaxy's extent and stellar density profile. More stars mean more planetary systems, more potential sites for life. If the Milky Way contains 400 billion stars instead of 100 billion, that's 300 billion more opportunities for habitable planets. Of course, we still don't know how common life is, but larger numbers increase the chances that we're not alone. The galaxy's size also affects its future beyond the Andromeda merger. In the very long term, trillions of years from now, the Milky Way, or its merger remnant, might merge with other members of the local group or even with galaxies from nearby groups. The galaxy's mass and size will influence how these future interactions unfold. Understanding the galaxy's size has practical implications too. It affects our searches for gravitational wave sources, for example. If the galaxy is larger, there might be more binary black holes or neutron star mergers within it. It affects predictions for how many pulsars should be detectable, how many supernovae should occur each century, how many exoplanets should exist. Most fundamentally, knowing the size gives us a sense of scale, a framework for understanding our place. We live in a galaxy that spans hundreds of thousands of light years, contains hundreds of billions of stars, and is embedded in a dark matter halo extending into the millions of light years. That's our cosmic address, our home in the universe. This knowledge shapes how we think about space exploration, about the search for life, about the future of humanity. A larger galaxy is a larger arena for future exploration and discovery, with more stars to study, more worlds to find, more mysteries to unravel. So the size of the Milky Way matters. It's not just a number in a textbook, it's a fundamental property that affects our understanding of where we came from, where we are, and where we might go. Measuring it has been one of astronomy's great achievements, and learning what it tells us is an ongoing adventure. Let's reflect on just how difficult it is to measure something from the inside, to appreciate the ingenuity required to determine the Milky Way's size from our embedded position within it. Imagine you're in a vast forest. Trees surround you in every direction, some close, some distant. Fog obscures your view beyond a certain distance. You want to determine the size and shape of the forest, but you cannot leave it, cannot see it from above, cannot even move very far from where you stand. This is the astronomer's predicament. Every distance we measure requires multiple steps, each with its own uncertainties. To measure the distance to a star in the halo, we might use an RR Lyrae variable as a standard candle. But calibrating the RR Lyrae luminosity requires knowing distances to nearby RR Lyrae stars, which might be done using parallax or statistical methods, each with uncertainties. These uncertainties compound. If your parallax distance has a 10% uncertainty, and the calibration adds another 10%, and the interstellar dust extinction adds 15%, your final distance might have an uncertainty of 25% or more. For an object you think is 100,000 light-years away, it might actually be 75,000 or 125,000. Now imagine doing this for millions of stars, trying to map the galaxy's structure, determining where different components end and begin. The challenge is immense. Different studies using different methods and different assumptions reach different conclusions. Progress comes from comparing results, understanding biases, refining techniques. Dust is a particular nuisance. It obscures our view across the galactic disk, absorbing and scattering light. Different wavelengths are affected differently, with blue light scattered more than red light. This makes stars appear redder and dimmer than they actually are, complicating distance estimates. Astronomers must correct for dust extinction, estimating how much dust lies along the line of sight to each star. This requires models of the dust distribution, often uncertain. Infrared observations help because dust absorbs visible light and re-emits it in the infrared, allowing the dust itself to be mapped. Another challenge is the sheer number of stars. The Milky Way contains hundreds of billions. We can only observe a tiny fraction individually. Most stars are too faint to detect from Earth, especially if they're distant or obscured by dust. Surveys like Gaia are remarkable for measuring 1 billion stars, but that's still less than 1% of the total. This means we must use statistical methods, observing representative samples and inferring properties of the whole population. If we survey a region of the sky thoroughly and count stars of different types, we can estimate the total number of such stars in the galaxy. But this assumes the surveyed region is typical, which might not be true. The Milky Way structure is irregular. There are spiral arms, the bar, the bulge, the warp in the outer disk. Different regions have different stellar densities, different dust contents, different compositions. Generalizing from one region to another requires careful modeling. Motion is another complexity. Stars are not stationary. They orbit the galaxy, each with its own velocity. Measuring these motions requires observing stars multiple times, sometimes over years or decades, to see how their positions change. This is astrometry, and it requires extraordinary precision. Gaia excels at astrometry, measuring positions to within microseconds of arc. This precision allows it to measure motions for stars tens of thousands of light years away. But even Gaia has limits. For the most distant stars, the motions are too small to measure reliably. Understanding the galaxy's rotation adds another layer. Stars at different distances orbit at different speeds. To determine how the galaxy rotates, we must measure velocities for many stars at many distances, then fit a rotation curve. This curve tells us about the mass distribution, including dark matter. But measuring velocities requires spectroscopy, spreading starlight into a spectrum and measuring Doppler shifts. This is time-consuming and requires larger telescopes than simple imaging. Spectroscopic surveys can observe millions of stars, but not billions. Combining astrometry, photometry measuring brightness, and spectroscopy gives the most complete picture. Gaia provides positions and motions. Ground-based surveys like SDSS and APOGEE provide spectroscopy. Together, they allow detailed mapping of the galaxy's structure and dynamics. Yet even with all this data, uncertainties remain. Different models fit the observations with different assumed galaxy properties. Degeneracies exist where multiple combinations of parameters give similar results. Distinguishing between them requires additional observations or constraints. This is the nature of science, especially astronomy. We work with incomplete information, making inferences, testing hypotheses, refining models as new data arrives. The Milky Way's size is not a single number but a range of values, with uncertainties that reflect our current knowledge limits. But those uncertainties have shrunk dramatically over the past few decades. Better telescopes, larger surveys, improved models, all have converged on a consistent picture. The Milky Way is large, larger than we thought, with its disk extending about 170,000 to 200,000 light-years, and its dark matter halo reaching several 100,000 to 1,000,000 light-years. The precision will continue improving. Future missions will measure more stars with better accuracy. Better theoretical understanding will reduce systematic uncertainties. Gradually, the error bars will shrink, and our knowledge will become more certain. But we'll always be inside, looking out, inferring structure from scattered data points. The challenge of measurement from within will never fully disappear. Yet that challenge is part of what makes the achievement so impressive. We've measured our cosmic home despite the difficulties, using human ingenuity to overcome natural obstacles. Behind every measurement, every discovery about the Milky Way's size are people. Scientists who spent careers building instruments, analysing data, developing theories. Let's think about the human side of this cosmic endeavour. The story of measuring the galaxy involves generations of astronomers, each building on the work of predecessors. Harlow Shapley in the early 20th century used globular clusters to estimate the galaxy's size and to determine that the Sun is not at the centre, but far out in the disk. This was revolutionary, displacing Earth and the Sun from any privileged position. Shapley's measurements were uncertain by modern standards, but they established the method. find objects whose distances you can measure, map their distribution, infer the galaxy's structure. Later, astronomers refined his techniques. Using better distance indicators, more objects, improved statistical methods, the development of radio astronomy in the mid-20th century opened new windows. Radio waves penetrate dust, revealing the galaxy's structure in hydrogen gas. By mapping the 21-centimetre line emission from neutral hydrogen, astronomers traced spiral arms and measured the galaxy's rotation. Vera Rubin's work in the 1970s on galaxy rotation curves, though focused on other galaxies, helped establish the existence of dark matter. Her careful measurements showed that galaxies rotate too fast to be held together by visible matter alone, leading to the dark matter hypothesis. This changed how we think about galaxy sizes, recognizing that most of a galaxy's mass and extent is invisible. The Hipparcos mission, launched in 1989, measured parallaxes for over 100,000 stars, creating the first accurate three-dimensional map of the solar neighborhood. This calibrated the cosmic distance ladder, improving distance estimates throughout the galaxy. Then came Gaia, a mission conceived in the 1990s, developed through the 2000s. Launched in 2013, thousands of scientists and engineers worked on Gaia, designing instruments, building spacecraft, planning observations, developing data processing pipelines. Gaia's data is so vast that processing it requires sophisticated algorithms and powerful computers. Teams of scientists work for years to calibrate measurements, remove instrumental effects, extract astrophysical parameters. The data releases, when Gaia's measurements are made public, are major events in astronomy. Individual scientists have dedicated careers to pieces of this puzzle. Some specialize in measuring stellar distances, others focus on galactic dynamics, using stellar motions to infer mass distributions. Still others build theoretical models, running simulations to interpret observations. There's collaboration across borders. The Gaia mission is European, but its data is used worldwide. American, Asian, Australian scientists all contribute to analysing Gaia data and to complementary observations with other telescopes. Science is a global endeavour. There's also competition. Different teams might have different models for the galaxy structure, different estimates for its size or mass. They publish papers, present at conferences, debate interpretations. This competition drives progress, as each team strives to make better measurements and more convincing arguments. But ultimately, the community works together. Conflicting results are resolved through better observations and deeper understanding. Consensus emerges gradually as evidence accumulates. The current picture of the Milky Way's size reflects the collective work of hundreds of scientists over decades. Behind the scientists are the institutions that support them: universities, research centres, funding agencies. Taxpayers in many countries fund space missions and telescopes. The search for knowledge about the Milky Way is a societal investment, supported because people value understanding our place in the universe. There's also a pipeline of students, young researchers who learn the techniques and carry the work forward. Every senior scientist trains the next generation, passing on knowledge and skills. This continuity ensures that projects spanning decades can succeed. The human element includes the mistakes, the false starts, the hypotheses that turned out wrong. Early estimates of the galaxy's size were off by factors of 2 or more. Some proposed structures, like certain spiral arms, turned out not to exist. Some distance measurement techniques proved less reliable than hoped. But mistakes are part of science. They teach us where our methods fail, where our assumptions are wrong. By learning from errors, we improve. The fact that our current understanding is different from past ideas doesn't mean past scientists were foolish. They worked with the information available, doing their best with the tools they had. And there's inspiration. Young people looking at images of the Milky Way, reading about galactic structure, feeling awe at the scale, might be inspired to become astronomers themselves. The quest to understand the galaxy's size is not just an intellectual exercise, but a source of wonder and motivation. For the scientists involved, there's the joy of discovery, the satisfaction of solving a puzzle, the pride of contributing to human knowledge. When a team publishes a paper showing the Milky Way is larger than thought, they're not just adding a fact to a database. They're changing how humanity understands its cosmic home. This human element is essential to remember. The Milky Way's size is not something that simply became known. It was discovered through effort, creativity, collaboration, and persistence. Real people, with lives and families and hopes, dedicated themselves to this work. Their efforts are part of the story. Even with all we've learned, significant uncertainties and mysteries remain about the Milky Way's size. Let's be honest about what we don't know and may never fully know, and find peace in that incomplete understanding. The exact size of the disk depends on how you define its edge. Different studies using different criteria find different radii. Some say 80,000 light-years from the centre, others say 100,000 or more. All are defensible, reflecting different definitions rather than contradictory measurements. This definitional ambiguity is not a failure, but a recognition that nature doesn't always provide sharp boundaries. The disk fades gradually. Choosing where it quote to is partly arbitrary. We can live with this ambiguity by being clear about our definitions and recognizing that different contexts might require different measures. The stellar halo's extent is even more uncertain. We've found halo stars over 200,000 light-years away, but how much farther does it extend? Are there halo stars at 300,000 or 400,000 light-years? Probably, but they're so sparse we haven't detected them yet. The halo might have no clear outer boundary, just ever-decreasing density. The dark matter halo's size is perhaps the most uncertain. We infer it from dynamics, but different methods give different results. Satellite galaxy orbits suggest one size. Rotation curve models suggest another. Simulations predict a range depending on assumptions about how the Milky Way formed. Current estimates place the virial radius, a theoretical boundary, at about 300,000 to 500,000 light-years. But this could be revised as we get better data. Future measurements of distant satellites or better determination of the Milky Way's mass might shift these numbers significantly. There's also the question of substructure. The dark matter halo probably contains subhalos, smaller concentrations of dark matter. Some might host dwarf galaxies, others might be dark, containing no stars. How many exist? How are they distributed? These questions affect the halo's detailed structure, even if not its overall size. Another mystery is the galaxy's merger history. We see evidence of past mergers in stellar streams, but we don't know all the details. How many satellites has the Milky Way consumed? When did the major mergers occur? How much mass was accreted? Reconstructing this history is detective work, piecing together clues from stellar populations, chemical compositions, and orbital distributions. Each stream tells part of the story, but the full narrative is still being written. Future discoveries will add chapters, and some parts might remain forever uncertain. The warp in the outer disk is not fully explained. It's probably caused by interactions with the Magellanic Clouds, but the exact mechanism is debated. Did a pass-close approach create the warp? Is it being maintained by ongoing interaction? Different models give different predictions. The bar in the inner galaxy is another area of uncertainty. We know it exists, but its exact dimensions, orientation and strength are still debated. The bar affects the orbits of stars and gas throughout the inner galaxy, influencing star formation and gas flows. Understanding it better would improve our understanding of the galaxy's structure. Dark matter itself is a profound mystery. We know it's there, but we don't know what it is. Discovering dark matter's nature would be one of the great scientific achievements, potentially revolutionizing physics. It might change how we think about galaxy halos, their formation, structure, and evolution. There are also possible surprises waiting. Every major survey has discovered unexpected features. The Sagittarius dwarf galaxy was discovered in 1994, astonishingly recent for such a large object. Newer, fainter satellites are still being found. There might be structures we haven't imagined, phenomena we haven't predicted. Living with uncertainty is part of being human. We want answers, clear facts, definite knowledge. But reality is complex, data is limited, and some things might be unknowable with current technology, or even fundamentally uncertain. Yet uncertainty doesn't mean ignorance. We know a lot about the Milky Way's size. The uncertainties are at the level of factors of 2 or less in most cases, sometimes just tens of %. This is far better than the complete ignorance of centuries past, and uncertainty drives progress. If we knew everything, there'd be nothing left to discover. The mysteries are opportunities, questions for future astronomers to answer, puzzles for new missions and theories to solve. There's a kind of beauty in the unknown. The universe retains its capacity to surprise us. We approach it with humility, recognizing that our current understanding is incomplete and might be revised. This openness to revision, this willingness to update beliefs based on evidence, is the essence of the scientific attitude. As we think about the Milky Way's size, we can hold both knowledge and uncertainty together. We know the galaxy is large, extending hundreds of thousands to perhaps 1 million light-years. We know its mass, its structure, its basic properties. But we don't know every detail, and some uncertainties might persist for decades or longer. That's okay. The partial knowledge we have is already remarkable, a testament to human curiosity and ingenuity. The mysteries that remain are invitations to keep exploring, to keep questioning, to keep seeking deeper understanding. Let's take a moment to try to grasp emotionally and intuitively just how big the Milky Way really is. Numbers like 200,000 light-years are easy to say, but almost impossible to truly comprehend. Let's try to find ways to imagine this scale. Light travels at about 300,000 kilometers per second, or 186,000 miles per second. In 1 second, light crosses the distance from Earth to the Moon about 13 times. In 1 year, light travels about 9.5 trillion kilometers, or 6 trillion miles. That's 1 light year. The nearest star to our Sun, Proxima Centauri, is about 4.2 light years away. Light from Proxima takes 4.2 years to reach us. When we look at Proxima, we see it as it was over 4 years ago. If Proxima exploded tomorrow, we wouldn't know for 4 years. The Milky Way's disk is about 200,000 light-years across. That means light from one side of the disk takes 200,000 years to reach the other side. 200,000 years ago, humans were still in the Stone Age. Neanderthals were alive. Agriculture hadn't been invented. All of recorded history, every civilization, every empire has occurred in less time than it takes light to cross our galaxy. Put another way, if you could travel at the speed of light, the fastest possible speed, it would take 200,000 years to cross the Milky Way's disk. The entire span of human civilization would pass multiple times during such a journey. Our fastest spacecraft, the Voyager probes launched in the 1970s, travel at about 17 kilometers per second. At that speed, crossing the Milky Way would take about 3.5 billion years. That's almost the age of Earth itself. The spacecraft would long since have ceased functioning, turned to cosmic dust, forgotten, while still barely making progress across the galaxy. The Sun orbits the Galactic Center at about 220 kilometers per second, much faster than any spacecraft we've built. Yet even at that speed, one orbit takes 225 million years. In Earth's 4.6 billion year history, the solar system has completed about 20 orbits. 20 times around the galaxy in all that time. Dinosaurs ruled Earth for about 165 million years, less than one galactic orbit. They lived and died, evolved from small creatures to giants and back, went extinct in a catastrophic asteroid impact, all within less than one trip around the galaxy. Humans, anatomically modern humans, have existed for maybe 300,000 years. In that time, the solar system has moved about 0.3% of the way around its orbit. we're still essentially where we started in galactic terms. All of human history is a tiny fraction of one cosmic year. If we scale the Milky Way down to the size of the United States, the solar system's orbit would be a circle about the size of Virginia. The solar system itself, out to the orbit of Neptune, would be about the size of a period on this page. Earth would be invisible, far smaller than an atom. On this scale, the distance to Proxima Centauri would be about the width of a comma. The distance to the centre of our galaxy would be about 800 miles. Perhaps the distance from New York to Chicago. The nearest large galaxy, Andromeda, would be on the Moon. These scaling exercises help a little, but they still don't capture the true vastness. Maybe it's better to accept that we can't really comprehend such scales intuitively. Our brains didn't evolve to think about light years and galactic dimensions. We evolved to navigate forests and savannas, to judge distances of meters and kilometers, not hundreds of thousands of light years. But we can understand it mathematically. We can work with the numbers, do calculations, make predictions, test them against observations. Our intuition might fail, but our reason does not. And maybe there's wisdom in that limitation. The vastness of the galaxy is humbling. It reminds us of our tiny place, our brief existence, the sheer scale of the cosmos compared to human life. We're motes in a vast structure, here for an instant in cosmic time. Yet we're also remarkable. We're the parts of the Milky Way that can think about the Milky Way. We're the galaxy studying itself. Despite our tiny size and brief lives, we can measure the whole, understand its structure, trace its history, predict its future. That's extraordinary. A species that has existed for a cosmic eye blink, on a planet that's a speck in the vastness, has figured out the size and structure of its home galaxy. We've done it from the inside without ever leaving, using light and gravity and mathematics. Perhaps the scale of the Milky Way is meant to inspire awe and humility together. Awe at the sheer vastness, the hundreds of billions of stars, the immense distances. Humility at our tiny place within it. Both feelings are appropriate, both are true. As you drift towards sleep tonight, you might imagine the Milky Way around you, above, below, in every direction. Stretching across hundreds of thousands of light years, you're embedded in it, part of it, made of matter that came from it. The galaxy is not just your home. In a sense, it's you, and you're it. Temporary patterns in the cosmic flow. Rest in that vastness. Let the scale wash over you without needing to fully grasp it. It's enough to know the galaxy is large, larger than we can imagine, and that we've measured it. That's a beautiful achievement for a small species on a small world. Let's turn our thoughts to the future, to what will happen to the Milky Way over billions of years, and how its size will change as time unfolds. For the next few billion years, the Milky Way will continue much as it is now. Stars will form in the disk's spiral arms, live their lives and die. Some will become white dwarfs, others neutron stars or black holes. The galaxy will slowly convert its gas into stars, gradually depleting the raw material for star formation. The galaxy will also continue to accrete smaller galaxies. The Magellanic Clouds will eventually merge with the Milky Way, perhaps in about 2 billion years. Their stars will be added to the Milky Way's halo. Their gas will replenish the disk, triggering new bursts of star formation. Other satellite galaxies will also be consumed over time. Each merger adds mass, increases the galaxy's size, and changes its structure slightly. The Milky Way will continue growing as it has been growing for billions of years, but the major event in the Milky Way's future is the collision with Andromeda. In about 4 billion years, the two galaxies will begin to interact. At first, they'll pass near each other, tidal forces pulling long streams of stars from each galaxy. The passage will disturb both disks, perhaps triggering bursts of star formation as gas clouds collide. Then they'll fall back together, colliding again more directly. Over billions of years they'll merge, their stars, gas and dark matter mixing together. The supermassive black holes at each galaxy's centre will spiral toward each other, eventually merging in a spectacular release of gravitational waves. The result will be a single large elliptical galaxy, sometimes nicknamed Milkomeda. Elliptical galaxies have no disk structure, no spiral arms, little ongoing star formation. They're smooth, spheroidal distributions of stars, mostly old and red. Milkomeda will be larger than either the Milky Way or Andromeda alone, containing all the mass from both. Its size will depend on how the merger unfolds, how much angular momentum is retained, how stars are redistributed. It might extend across several 100,000 light-years or more. By that time, Earth will likely be uninhabitable, if it still exists. The Sun will have evolved into a red giant, expanding to perhaps the orbit of Mars, incinerating the inner planets. Life on Earth, if any survives the Sun's evolution, will have to have found refuge elsewhere. But the night sky will be spectacular during the merger. For any observers on surviving worlds, Andromeda will grow larger and larger over millions of years, eventually filling a significant portion of the sky. The collision will create tidal tails, arcing streams of stars visible as enormous structures in the night sky. After the merger, over tens of billions of years, Milkomeda will slowly fade. Star formation will largely cease as gas is used up or heated to temperatures too high to collapse. The remaining stars will age, the massive ones having long since died, leaving only long-lived red dwarfs and the remnants of dead stars, white dwarfs, neutron stars, black holes. Over trillions of years, stars will be slowly ejected from the galaxy through gravitational interactions, random encounters with other stars that transfer enough energy to escape. The galaxy will gradually evaporate, losing stars to intergalactic space. The central supermassive black hole will grow slightly by accreting stars that pass too close. But most stars will simply orbit for trillions of years, never coming close enough to be captured. Eventually, perhaps 10 to the 20 years from now, an incomprehensible span, even the longest-lived stars will burn out. The galaxy will be dark, filled only with stellar remnants and the supermassive black hole. It will still be massive, still gravitationally bound but invisible, a dark island in an expanding universe. And then, over even longer timescales, the protons in dead stars might decay, if current theories are correct. Matter itself might dissolve, leaving only black holes and radiation. The black holes will slowly evaporate through Hawking radiation, taking 10 to the 100 years or more to disappear completely. At that point, nothing recognizable as a galaxy will remain. Just dilute radiation in an expanding, cooling universe. The Milky Way, Andromeda, Milkomeda, all will be gone, returned to the entropy from which they came. But these timescales are so vast as to be almost meaningless. 10 to the 100 years is a one followed by 100 zeros. It's longer than the current age of the universe by factors that make quote 4 seem tiny. For all practical purposes, it's eternity. The future relevant to us is the next few billion years. In that time, the Milky Way will continue to be a vibrant, active galaxy. Stars will form, planets will orbit, and perhaps life will flourish on countless worlds. The galaxy's size will grow through accretion and eventually through the Andromeda merger. For any civilizations that might exist in the galaxy, including descendants of humanity if we survive, the growing size means more space to explore, more resources to access, more worlds to inhabit. A larger galaxy is a larger stage for cosmic drama. The Milky Way's future, like its past, is one of growth and change. The galaxy is not static. It's evolving, and its size is part of that evolution. Measuring the galaxy's current size is measuring a snapshot in a long history, a moment in a story that spans from the distant past to the unimaginable future. As we contemplate this future, we can feel both insignificance and significance. Insignificant because the galaxy will outlast us by billions of years, continuing long after human civilization is forgotten. Significant because we're here now, in this moment, able to understand and appreciate the galaxy's story. As we move into these final contemplative chapters, let's think about numbers not just as facts, but as a kind of poetry, as expressions of beauty and wonder. 200,000 light years, the approximate diameter of the Milky Way's disk. This number represents uncountable hours of observation, decades of work, thousands of scientists across generations. But it's also beautiful in itself, a measure of vast distance expressed in the speed of light. 100 billion to 400 billion, the estimated number of stars in the Milky Way, each one a sun, potentially with planets, possibly with life. The number is so large it loses meaning, yet each unit is a specific star, a distinct object with its own properties and history. 26,000 light years, our distance from the Galactic Center. We're embedded halfway out, in a quiet spiral arm, positioned such that we can observe both the inner and outer galaxy. This particular number defines our vantage point, our specific location in the cosmic vastness. 1 trillion solar masses, the approximate total mass of the Milky Way, including dark matter. Most of this mass is invisible, known only through its gravitational effects. The number quantifies something we cannot see, making the invisible concrete through measurement. These numbers are not arbitrary. They're discovered, measured, refined over time. They describe objective properties of the universe, independent of human observation, yet they're only known because humans have observed and calculated. There's poetry and precision too. Gaia measures stellar positions to within 10 microarc seconds. That's like measuring the width of a human hair from the distance of the moon. Such precision is achieved through careful engineering, sophisticated algorithms, and the determination of countless people. The numbers connect us to the cosmos. When we say a star is 10,000 light years away, we're linking our small planet to that distant sun through the concept of distance. We're creating a relationship, a mental connection spanning vast physical separation. Numbers also reveal patterns. The rotation curve of the galaxy, plotting velocity versus distance, shows a flat or rising profile at large radii. This pattern is evidence for dark matter, a discovery made through careful measurement and graphing. The ages of stellar populations, inferred from their colours and brightness, reveal the galaxy's history. Old red stars in the halo tell of ancient formation. Young blue stars in spiral arms speak of ongoing starbirth. Each population has characteristic ages, measured in billions of years, written in the light they emit. Chemical abundances measured through spectroscopy tell stories of enrichment. The fraction of iron in a star indicates how many previous generations of stars lived and died before it formed. Higher iron means more stellar cycles, a later formation time. These numbers are a language, a way the universe speaks to those who know how to listen. The light from distant stars carries information encoded in wavelengths, intensities, and spectra. By measuring and interpreting these numbers, we decode the messages. There's humility in working with numbers this large. 100 billion stars is beyond visualization. We can write the number, calculate with it, but we cannot picture it. The galaxy's size exceeds our intuitive grasp, reminding us that reality is larger than our imagination. Yet there's also power in abstraction. We can understand mathematically what we cannot perceive directly. We can reason about the invisible dark matter, calculate its distribution, predict its effects, all through numbers and equations. Mathematics extends our reach beyond our senses. The uncertainties in numbers are also meaningful. When we say the dark matter halo extends to perhaps 1 million light years, with an uncertainty of a few 100,000, that uncertainty represents the current limits of knowledge. It's an honest admission of what we don't know precisely, even as we know approximately. Numbers change as knowledge improves. Older textbooks might give the Milky Way's diameter as 100,000 light years. Newer ones say 170,000 or 200,000. This evolution shows science in action. updating to reflect better observations. But the earlier numbers weren't wrong in a meaningful sense. They were the best estimates available at the time. Science is cumulative, building on previous work, refining rather than replacing. The galaxy was always the size it is. We're just getting better at measuring it. There's beauty in this progression, in the gradual convergence toward truth. Each generation of astronomers contributes, moving the measurements closer to reality. We may never know the exact size to infinite precision, but we get closer with each improvement in technology and technique. Numbers also democratize knowledge. Anyone can understand that 200,000 light-years is larger than 100,000. You don't need advanced training to appreciate the scale. Numbers make cosmic knowledge accessible, translatable into forms anyone can grasp at some level. As we think about the numbers describing the Milky Way's size, we can appreciate them as both scientific facts and as expressions of human achievement. Each number represents a question answered, a mystery partially solved, a step toward understanding our cosmic home. The poetry of numbers is that they make the abstract concrete, the vast comprehensible, the invisible measurable. Through numbers we connect with the galaxy, making it real in a way that mere words cannot. The Milky Way is not just large, it's specifically, measurably, beautifully 200,000 light-years across. Let's think about what it means that we now know the size of the Milky Way, how this knowledge refines our cosmic address, our place in the universe. Before modern astronomy, our address was simple: Earth. Later, it became Earth, the third planet from the Sun. Then, Earth, orbiting a star in the Milky Way. Now we can be much more specific. Earth, third planet from the Sun, which orbits 26,000 light-years from the Galactic Center in the Orion Spur, a partial spiral arm between the Perseus and Sagittarius arms, in a galaxy spanning about 200,000 light-years. This precision matters. It locates us not just qualitatively but quantitatively. We're not just somewhere in the galaxy, we're specifically positioned, measurably distant from the center, embedded in a particular structure. Our address extends further. The Milky Way is part of the Local Group, a collection of about 100 galaxies spanning 10 million light-years. The Local Group is part of the Virgo supercluster, a larger structure of galaxy groups and clusters extending across 100 million light-years or more. Even that's not the end. The Virgo supercluster is part of Laniakea, a vast supercluster structure identified in 2014, spanning 500 million light-years. Laniakea is defined by the pattern of galaxy motions, all flowing toward a region called the Great Attractor. And Laniakea is just one structure among many in the observable universe, which extends about 93 billion light-years across due to the expansion of space. Our cosmic address goes from a planet to a solar system, to a spiral arm, to a galaxy, to a group, to a supercluster, to a vast filament in the cosmic web. Each level of this address is meaningful. Being on Earth rather than Jupiter means liquid water and a life-sustaining environment. Being in the habitable zone of our star means moderate temperatures. Being in a quiet spiral arm might mean fewer supernovae. Threats and more stable conditions for life. Being in a large galaxy like the Milky Way means access to heavy elements created in earlier generations of stars, the carbon and oxygen and nitrogen needed for life. Small galaxies might not have had enough star formation to enrich their gas sufficiently. Being in the Local Group rather than isolation means we'll eventually merge with Andromeda, potentially affecting the long-term future of any civilizations that might exist. Being in Laniakea means we're part of a larger structure, connected to thousands of other galaxies through gravity and shared motion. Knowing the Milky Way's size refines this address. It tells us how large our immediate cosmic home is, how far we'd need to travel to leave it, effectively impossible with current technology, how many stars share our galaxy, hundreds of billions, how much mass surrounds us, trillions of suns worth. This knowledge contextualizes human existence. We're residents of a vast structure, so large that light takes 200,000 years to cross it, so massive that it contains enough matter to make hundreds of billions of stars. Yet we're just one planet among untold trillions that might exist in the galaxy. The cosmic address also connects us to a history. The Milky Way is 13 billion years old or more, formed from gas clouds in the early universe. Our solar system is 4.6 billion years old, formed from material enriched by earlier generations of stars. Earth is 4.5 billion years old. Life on Earth began perhaps 4 billion years ago. Humans, anatomically modern, are 300,000 years old. Civilization is perhaps 10,000 years old. Recorded history is about 5,000 years. We're newcomers to a galaxy that has been evolving for eons. Yet in that brief time, we've figured out our address. We've measured the galaxy, determined our position, understood the structure we're embedded in. This is remarkable, a testament to human curiosity and capability. Our cosmic address is also humbling. We're tiny, a negligible fraction of the galaxy's mass and volume. Our planet is a speck, our existence a moment. In the cosmic scheme, we might be utterly insignificant. But significance is not only about size or duration. Perhaps it's about complexity, consciousness, understanding. Humans are among the most complex structures we know of, our brains containing billions of neurons creating thoughts and feelings. Consciousness itself might be rare in the universe, and if we're one of the few, or perhaps only species that can contemplate the galaxy's size, that gives us a unique significance. We're the way the Milky Way knows itself. The galaxy has spent billions of years evolving, and now, in us, it has achieved self-awareness. This perspective shifts how we think about our address. Yes, we're small and temporary, but we're also remarkable, complex, conscious. Our address is not just a set of physical coordinates, but a statement about what we are. Conscious beings in a vast cosmos, understanding our place through science and reason. As we drift towards sleep, we can hold this cosmic address in mind. Earth, solar system, Milky Way, local group, Laniakea, observable universe. Each level nest within the next, a hierarchy of structures from the planetary to the cosmic. And we're here now, in this moment, aware of this address, contemplating the distances and structures that define our place. That awareness is precious, a brief flicker of consciousness in a vast, mostly unconscious cosmos. Rest in that awareness, in the knowledge of where you are, in the wonder of understanding your cosmic home. When you look up at a clear dark night sky, far from city lights, you see the Milky Way as a band of light stretching across the heavens. Knowing what you now know about the galaxy's size and structure, that band takes on new meaning. Let's contemplate the night sky with our new understanding. Each point of light you can see with your naked eye is a star in the Milky Way, almost certainly within a few thousand light years of Earth. The farthest individual stars visible to the naked eye are perhaps 15,000 light years away, less than 1/10 the distance to the Galactic Center. The rest of the galaxy is too distant or too obscured by dust for its individual stars to be visible. The band of the Milky Way, though, contains billions of stars, so many and so distant that they blend together into a diffuse glow. You're looking edgewise through the disk, seeing the combined light of countless stars too faint to distinguish individually. Different parts of the band have different brightnesses. Toward the constellation Sagittarius, the Milky Way is brightest because you're looking toward the Galactic Center, where stars are most densely packed. Toward Auriga and Perseus, you're looking outward toward the disk's edge, and the band is fainter. Dark patches in the Milky Way are not gaps where there are no stars. They're dust clouds blocking our view of stars behind them. The Great Rift, a dark band running along the Milky Way in Cygnus and Sagittarius, is a series of overlapping dust clouds obscuring the background stars. Knowing the galaxy is 200,000 light years across reframes what you're seeing. The band you observe represents only a small fraction of the galaxy's extent. Most of the structure is invisible, either too distant, too obscured, or too faint to see. If you could see all wavelengths, not just visible light, the Milky Way would look different. In infrared, dust glows, revealing warm clouds throughout the disk. In radio, hydrogen gas traces the spiral arms. In X-rays, hot gas and energetic objects like neutron stars and black hole systems shine. In gamma rays, exotic processes like matter-antimatter annihilation create a diffuse glow. But in visible light, you see only part of the story, a beautiful but incomplete picture. The stars you see are the tip of the iceberg, a tiny sample of the hundreds of billions that exist. If you were in intergalactic space, millions of light years from any galaxy, and looked back at the Milky Way, you'd see it as a spiral, arms winding outward from a bright central bulge, much like the images of other galaxies we've taken with telescopes. It would be beautiful, a grand designed spiral glowing with the light of hundreds of billions of stars. But you'd miss the experience of being inside, of seeing it as a band across the sky, of having it surround you in every direction. There's a unique beauty in our embedded perspective, seeing the galaxy from within rather than without. The night sky connects us to the past as well. The light from distant stars takes time to reach Earth. When you see a star 1,000 light years away, you're seeing it as it was 1,000 years ago. The star might have changed, evolved, even died in the intervening time, but the light showing its earlier state is just now arriving. The band of the Milky Way contains light from billions of stars at various distances, all showing those stars as they were hundreds or thousands of years ago. You're looking at a historical record, a collection of past moments, all arriving simultaneously at your eyes. Ancient peoples looked at the same sky, saw the same Milky Way band, wondered about its nature. They created myths, stories about rivers of milk, paths of spirits, bridges between earth and heaven. They didn't know they were seeing a galaxy from the inside, but they recognized it as something special, something worthy of wonder. Now we know what it is. We've measured it, mapped it, understood its structure. But knowing doesn't diminish the wonder. If anything, understanding enhances it. The band of light is not just beautiful, it's hundreds of billions of stars in a vast structure we call home. When you look at the night sky, you can think about the galaxy's size, about the 200,000 light years the disk spans, about the million light years the dark matter halo might extend. You can think about your position, about halfway out from the centre, in a partial spiral arm, looking through the disk at your galactic neighbours. You can think about the future, about the eventual merger with Andromeda, about the slow evolution of the galaxy over billions of years. You can think about the past, about the formation from gas clouds 13 billion years ago, about the accumulation of matter through mergers, about the gradual enrichment of gas with heavy elements. All of this history and future, all of this structure and scale is present in the band of light above you. The Milky Way is not just out there in space, it's here, surrounding you, containing you. You're part of it, made of matter that came from it, living on a world that formed from its gas and dust. The night sky is an invitation to contemplate this connection, to feel your place in the cosmic structure, to appreciate both the vast scale and your participation in it. Look up when you can, away from lights, and see the Milky Way. Know that you're looking at your cosmic home, a structure we've finally measured. A galaxy far larger than earlier generations realized. Rest in that knowledge, in the beauty of the night sky, in the connection between you and the stars. Let it be a peaceful thought as you drift towards sleep. The Milky Way above you, around you, part of you. Let's gather together the strands of what we've learned on this journey, reflecting on the key insights about the Milky Way's size and what they mean. We've learned that the Milky Way is far larger than we thought even a few decades ago. The disk extends to at least 80,000 light-years from the centre, probably farther when you include the warped outer regions, making the total disk diameter 170,000 to 200,000 light-years or more. We've learned that the stellar halo reaches past 200,000 light-years, traced by distant stars and stellar streams from disrupted satellite galaxies. These streams are fossil records of past mergers, telling the story of how the Milky Way has grown by consuming smaller galaxies. We've learned that the dark matter halo, invisible but massive, extends even farther, perhaps to 300,000 to 1,000,000 light-years from the Galactic Center. This halo contains most of the galaxy's mass, dominating the gravitational potential and shaping the orbits of everything from disk stars to distant satellites. We've learned that the Milky Way is one of the largest spiral galaxies in our cosmic neighbourhood, comparable in size to Andromeda, larger than the vast majority of galaxies in the universe, though not among the very largest elliptical giants. We've learned how these measurements were made, through careful observation of stellar positions and motions, through mapping of gas and dust, through tracking of satellite galaxies, through the patient accumulation of data from many telescopes and surveys over many years. We've learned that size is not a simple concept. Different definitions, the edge of the disk, the extent of the halo, the reach of gravitational influence, give different values. The galaxy doesn't have a sharp boundary but gradually fades into intergalactic space. We've learned that the Milky Way is still growing, still accreting smaller galaxies, still evolving. It's not a static structure but dynamic, changing over time, larger now than in the past, destined to grow even larger when it merges with Andromeda. We've learned that most of the galaxy is dark matter, invisible substance known only through its gravitational effects. Understanding this dark component is crucial to understanding the galaxy's full extent and mass. We've learned about the challenges of measuring from inside, of determining the size of something we're embedded within, of using indirect techniques and statistical methods to infer structure we cannot see directly. We've learned that uncertainty remains, that different studies give somewhat different results, that refinements will continue as observations improve, but the uncertainties are now relatively small compared to past decades, when estimates varied by factors of 2 or more. We've learned that this knowledge connects to broader cosmology, to galaxy formation theory, to the nature of dark matter, to predictions for the future merger with Andromeda. The Milky Way's size is not an isolated fact, but part of a network of related knowledge about how galaxies form and evolve. We've learned that human ingenuity can overcome seemingly impossible obstacles. Measuring the galaxy from inside seemed like it might be forever beyond our reach, but through clever techniques and persistent effort, we've done it. We've learned about the scientific method in action, how observations and theory work together, how different techniques cross-check each other, how consensus emerges gradually from accumulating evidence. We've learned about the human side of science, about the generations of astronomers who contributed to this knowledge, about missions like Gaia that required decades of planning and years of operation, about the collaborative nature of modern science. We've learned to appreciate scale, even if we can't fully comprehend it intuitively. 200,000 light-years is a distance we can calculate with but not visualize, yet we can appreciate its vastness, its far exceeding of human scales, its humbling magnitude. We've learned that knowledge brings both answers and new questions. We know the Milky Way's size better than before, but this knowledge raises questions about dark matter's nature, about the details of past mergers, about the exact dynamics of the disk's warp, about numerous other topics. We've learned that the quest for knowledge is ongoing, that current understanding is provisional, that future discoveries will refine and possibly revise what we think we know. Science is a process, not a destination. Perhaps most importantly, we've learned that we live in a remarkable galaxy, one of the giants of the local universe, a vast structure containing hundreds of billions of stars, extending across hundreds of thousands of light years, our cosmic home that we've finally measured. This knowledge enriches our understanding of our place in the universe. We're not just somewhere in space. We're specifically located in a well-understood structure whose size and mass and extent we've determined. We know our cosmic address with precision our ancestors couldn't have imagined. As we approach the end of our journey, we can rest in this knowledge, in the satisfaction of understanding, in the wonder at what humans have achieved. We've measured the Milky Way, our home among the stars, and found it large and magnificent, a galaxy worthy of awe and appreciation. In these final quiet moments together, let's simply rest in the vastness of the Milky Way, letting go of details and numbers, just feeling the scale and beauty of our cosmic home. Imagine yourself floating in space, far from Earth, looking back at the galaxy. You see it as a spiral, arms winding outward from the centre, glowing with the light of billions of stars. It's beautiful, majestic, serene. You notice details, bright blue regions where young stars are forming, reddish clouds of glowing gas, nebulae where chemistry and physics create luminous sculptures, dark lanes of dust tracing the spiral arms. The galaxy rotates slowly, imperceptibly at this scale, but you know that it's turning, that stars are orbiting the centre, that the whole structure is a vast, graceful dance of matter and gravity. You see the central bulge, bright and dense with old stars. You see the disk extending outward, thinning gradually, fading into the darkness. You imagine the halo surrounding it all, invisible stellar populations and dark matter extending far beyond the visible light. You think about the 200,000 light-years the disk spans, about the hundreds of billions of stars it contains, about the trillion solar masses of total mass including dark matter. The numbers float through your mind without demanding attention, just markers of scale. You think about your place in this structure. Somewhere in that disk, in one spiral arm, around one ordinary star, is a small planet. Earth. Home. Your entire world, all of human history, every person you've ever known, all existing on that tiny speck within the vastness. There's no need to feel small or insignificant. You're part of this structure, made of its matter, evolved from its chemistry. The galaxy is not separate from you. In a real sense, you are the galaxy, a small part of it, briefly conscious, briefly capable of contemplating the whole. Let yourself rest in this perspective. You don't need to understand all the details. You don't need to remember the numbers. Just feel the vastness, the beauty, the connection. The Milky Way has been here for 13 billion years, evolving slowly, forming stars and planets, and perhaps countless other worlds with life. It will be here for billions more, gradually changing, eventually merging with Andromeda, but persistent, enduring, vast. Your life is brief by comparison, a single moment in the galaxy's long story. But it's your moment, your time to exist, to be aware, to wonder. That's enough. That's everything. As you prepare for sleep, let the image of the galaxy fill your mind. See it as a spiral of light in the darkness, beautiful and serene. Feel yourself as part of it, connected through matter and energy and history. Breathe slowly, deeply. Let your body relax completely. Let your thoughts drift like stars in the galactic current, moving in vast orbits, patient and unhurried. The Milky Way will be there tomorrow, unchanged in any human timescale. The stars will shine. The galaxy will rotate. The structure will persist. You can return to contemplating it any time, but for now, just rest. Rest in the vastness. Rest in the beauty. Rest in the knowledge that you're home, embedded in a structure we've finally measured, a galaxy far larger and more magnificent than earlier generations knew. Let sleep come naturally, gently, like starlight falling through space, unhurried, peaceful, inevitable. There's nowhere you need to be, nothing you need to do. Just rest in the Milky Way, your cosmic home, vast and beautiful and finely measured. Close your eyes, if they're not already closed. Breathe. Be still. The galaxy surrounds you, contains you, is you. Rest in that truth, in that connection, in that vastness. Rest and sleep, peaceful and content, under the stars of our home galaxy. Thank you for staying with me through this long, gentle journey through the Milky Way. exploring the question of how big our home galaxy really is. We've spent 2.5 hours together, moving from measurements and methods through scale and structure to meaning and wonder. I'm grateful you chose to spend this time contemplating our cosmic home. We've travelled together through many ideas. We explored how astronomers measured the galaxy from inside, discovered it's far larger than we thought, understood the disk, halo and dark matter components, compared the Milky Way to other galaxies, and reflected on what this knowledge means for our understanding of our place in the universe. And now, as we reach the end, let's return to the simple fact at the heart of our journey. We finally know how big the Milky Way is. The disk extends about 200,000 light-years across. The stellar halo reaches past 200,000 light-years. The dark matter halo might extend to 1,000,000 light-years or more. These are not guesses or rough estimates. They're measurements, determined through careful observation and analysis. The answer to how big the Milky Way is, as honestly as I can give it, is that it depends on what you're measuring. The disk is 170,000 to 200,000 light-years across. The overall gravitational influence extends to perhaps 1,000,000 light-years. Different components have different extents, but all are far larger than the 100,000 light-year estimates from older textbooks. We live in a galactic giant. If you enjoyed this slow drift through galactic measurements and cosmic scale, a like and subscribe helps others find these calm explorations. And if you have thoughts about the Milky Way, about what we've discussed, or reflections on our cosmic home, the comments are a space for sharing. To those already part of this community, thank you for being here, for bringing your curiosity to these explorations of our universe. Wherever you are in the world right now, I hope you found some peace in this journey. I hope your breathing has slowed, that the day's concerns have faded to background, that your thoughts have turned to the cosmos and the remarkable galaxy we call home. I hope you feel connected to something larger, to the vast structure that surrounds us. Look up at the stars if you can see them from where you are, or imagine them if you can't. That band of light crossing the sky, or the individual stars scattered across the darkness, those are your galactic neighbours, fellow travellers in the Milky Way's long journey through time. All those stars are part of a structure we've measured, a galaxy extending across 200,000 light-years, containing hundreds of billions of suns, embedded in a dark matter halo reaching toward 1,000,000 light-years. It's vast, far larger than human minds can fully comprehend, yet we've determined its size through mathematics and observation. The mystery of how we're able to measure something we're inside of has been solved through human ingenuity. The question of whether the Milky Way is large or small has been answered. It's one of the giants of galaxies, larger than most, comparable to our nearest large neighbour Andromeda. But beyond the facts and measurements, beyond the numbers and techniques, there's wonder. Wonder at the sheer scale, at the billions of stars, at the vast distances. Wonder at our ability to understand it, to map it from the inside, to determine its extent despite being embedded within it. Wonder at our cosmic home, this magnificent spiral that contains us. Sleep well tonight. Dream of spirals winding through space, of billions of stars in graceful orbits, of dark matter halos extending into the vastness, of a galaxy far larger than earlier generations knew. Dream of measurements made from the inside, of light travelling across 200,000 light-years, of our place in this vast structure. Dream of future discoveries that will refine these measurements, of the eventual merger with Andromeda, of the slow evolution of our galaxy over cosmic time. Dream of the human story of measurement and discovery, of the scientists who dedicated careers to understanding our cosmic home. Dream peacefully, knowing that the Milky Way surrounds you, that you're part of it, that you're home in a structure we've finally measured. The galaxy is vast, but it's knowable. It's complex, but it's understandable. It's magnificent, and we live within it. Good night. Rest in the vastness of the Milky Way, in the knowledge of its size, in the wonder of its scale. Let your thoughts drift like stars in galactic orbits, peaceful and unhurried. Sleep well, and when you wake, you'll still be here, in our home galaxy, vast and beautiful and finely measured. Good night.